Well, I think this is this is the last lecture for the summer school. So before I start my lecture, maybe let's thank together for organizers. This is a wonderful summer school. Yeah, okay. So today I'm going to finish the calculation of the configuration space integral. So let's recall what we did last time. Last time we introduced the so-called handle replacement construction. So basically there are two types. Type 1, we replace this type 1 handle body into a different type 1 handle body with a different handle body, which is the complement of the long Baromean ring. Okay, and we also have a type 2 handle replacement, which replaces H2. Which is S1 cross D3, boundary connect is on S1 cross, it's S2 cross D2. We replace it into a whole family of handle bodies, so H prime to theta. Well, theta belongs to S1, okay? So so last time we used this notation H prime to theta to denote the union of theta in S1 of all these. Okay, so this is really a family over S1. Okay, and today I'm going to unify the notation. Let me also define H1 theta. It's just a disjoint union of H1. Okay, so let me just say it. Okay, H1 0, H1. Okay, well, this is just defined to be H1, the original handle body, and this is defined to replace the handle body. Okay, and I treat this as a family over S0. Okay, where S0 is just consists of 2 points. 0 and 1, okay? So this is just to unify these two notations, okay? So here we have a family over S1, here we have a family over S0, okay? Right, and let's recall that there exist submanifolds. There exist some submanifolds F1 prime, F2 prime, F3 prime contained in this H1 prime contained in this handle body, such that the triple intersection number equals 1, and they satisfy some boundary condition. Boundary F1 prime equals blah blah blah, boundary F2 prime equals. So let me not write down the boundary condition again. Okay, so this was done yesterday. Okay, all right, and so we also have the standard. Okay, so this is included in H1 prime. We also have the standard submanifold F1, which is a point cross D3. F2, another point cross D3, and F3. A point cross D2. These are standard submanifold contained in H1. Okay, remember that H1 is just this handle body, so I just fix a point here and get embedded three-dimensional disk. I fix another point, get another D3, and fix another point and get D2. Okay, and this gives us F1, F2, F3. They have the same boundary. Okay, so yeah, so maybe let me just say. Okay, All right, and what do we do? Now, let's consider so first we call that, let me give a general setup. Suppose you have a proper embedding of a manifold into another manifold. Then one can always define a so-called Tom form, which is that there exists a closed differential form. Let me denote it by mu n, which is belongs to omega m minus m m, supported on a tubular neighborhood of the submanifold, and such that this in the de Rham cohomology, it represents the Poincare ideal of this submanifold. Okay, this is the Tom form. So given any submanifold, I can construct some differential form supported in a tubular neighborhood of this submanifold, which represents the Poincare ideal of the submanifold. This submanifold can have boundary. Okay, yeah. All right. So let's apply this construction to the following submanifolds. Okay. So we define mu1 to be the Tom form for F1 disjoint union F1 prime. So this will be a one form of this H2 top prime 1. Okay, remember that this is just a disjoint union of H1 with H1 prime. So you have this F1 embedded into H1 and F1 prime into H1 prime. Okay, so this is a one form. Mu2 equals mu F2. So another one form. And mu3. Omega 2. Okay, this is a two form because F3 is 2 dimension, so codimension equals 2. So its Tom form is also half degree 2. Okay, and from this condition, we see that, okay, so first of all, what's the condition? Okay, so this, okay, so F1, F2, F prime, the triple intersection between these three surfaces equals 1, while the triple intersection of this standard, these three surfaces is just empty. Okay, so from this you translate that, and you get, what we get is the following. Mu1 wedge mu2 wedge mu3 equals 1. Okay, this will be crucial in our calculation. Okay, so the integration of these three forms just equal 1 because these three, the triple intersection number of these three submanifolds equal 1. Okay. And similarly, we have embedded submanifolds G1 prime, G2 prime, G3 prime embedded into the into this family H2, right? So so what we can do is like let's define lambda 1 to be the Tom form for G1 prime. Did I use tilde? Let me see. Oh no, I didn't use. Okay. So G1 prime, G2 prime. So okay. So this is let me see. This is a two form. Or this is a one form on this family of handle bodies. And this is a two form, and this is also a two form. Okay, so this is a family over S1 whose fiber is 4-dimensional handle body. So the total dimension is 5-dimensional. Okay, and from this condition, we can also conclude that okay, just because the triple intersection number equal 1. Good. So these are some construction of differential forms. Yeah. Any questions so far? We just use this submanifold to construct forms.
Total space H tilde 2.
Mm-hmm.
How exactly do you build it?
It's the H tilde 2. It's the H2. Prime theta. Okay, so you start with the so-called I2 theta prime, which is a family of embeddings of I2, I1, I1 into I4. This is the so-called long Baromean family. And you take the complement and get this family of handle bodies.
They're all embedded in I4.
Yeah, so you take I4 cross S1 and you remove a tubular neighborhood of that.
So is lambda 3 and omega 1?
Lambda 3, omega, sorry, what's omega? Sorry, where is this one?
No, I mean you have too much. You have omega 1, omega 2, omega 2.
It's 5-dimensional because, yeah, this is 5-dimensional because the fiber is 4-dimensional and base is 1 dimension.
Oh, okay.
So yeah, 1 plus 2 plus 2 equals 5, yeah. Okay, right, so these are some differential forms we defined on the handle bodies. What are we going to do with it? Okay, so yeah, let me erase this. So, okay, to make our life easier, we are going to focus on trivalent graphs, gamma, which has no self-loop, no multiple edges, no orientation reversing isomorphisms. Okay, orientation reversing means that on the set of edges is an order permutation. Okay, so one can, it's not hard to prove that once your graph has an orientation reversing isomorphism, the corresponding integral will just be 0. So let's just consider this. Okay, and we embed gamma in a standard way into D4, and which includes into S4. Okay, so a typical example is like this. Okay, this is the complete 4-valent graph, and this is the complete 3-valent graph with 4 vertices, and we just orient each edge. This is gamma, and as we mentioned, we replace the middle portion of each edge into a Hopf ring, and get gamma prime, and take the tubular neighborhood of each component. Each give us a handle body. Okay, so we have this 4 handle body I draw here. Okay, yeah. So this is what we did yesterday, and okay, so we are going to order the vertices such that the first k vertices are of type 2. I will review what do I mean by type 2, and the rest are type 1. Okay. And the edges, since it's a trivalent graph, there are 3k edges. Okay. So what do we mean by type 1 and type 2? Type 1 simply means that you have 2 incoming edge, one going edge, and type 2 means 1 incoming edge, 2 outgoing edge. Okay, so there are 2 types of vertices. For example, here 1 and 2 they are type 1, and 3, 4 they are type 2. Okay, and H1, Hi. Okay, let me see. Now, as you can see, gamma prime is no longer connected. Its connected component 1 correspond to the vertices of your gamma. So I belongs to 1 less equal than I less equal than 2k gamma I prime. Well, gamma I prime, there are two possibilities. One is like this. This is type 1. And type 2 is like this. Okay, right? These are the two possibilities. We are going to fix an order on the three edges. It's flipped. Give me a second. Type 1, type 2. Oh, let me see. Oh, yes, this is type 2. Sorry, this is type 1. Yeah, 6. Yeah, all right. And I'm going to denote. Okay, so this is vertex I. I'm going to denote this sphere by SI1, SI2, SI3, SI1, SI2, SI3. Okay. So here, since I is type 1, so here I is between 1 and k. And for this picture, because it's type 2, we have k plus 1 less equal than I less equal than 2k. Last line. Oh, okay. Sorry. Yeah, you're right. So here is k type 2 should be, and this is type 1. In which example? In this example? The first two is type. Let me see. Okay, I guess I messed up with the convention. Well, anyway, so let's, yeah, so maybe just relabel these numbers, and we will stick to this convention, okay? All right, yes. So, what do we want to do? Okay, yeah. So we denote the tubular neighborhood of the ith component by hi, and this is diffeomorphic to h1 if I is greater or equal than k plus 1, and h2 if it is type 2. Okay, so we have two types of handle bodies here. We also let h0 to be the complement of all these handle bodies. So it's okay. We also use it to denote h0 prime. Okay, so these are just some handle bodies. And yesterday we did some handle body replacement, right? So we replace one of these handle bodies into h1 prime or h2 prime, and get a family of 4 manifolds. Right? Yes. Yeah. So today I'm going to do a slightly funny thing, which is yesterday I constructed a family over torus, right? But today I'm going to construct a slightly different family for the computation. I mean, I will construct a family over a disjoint union of torus. Why do I do that? Okay, so let me define a family. Okay. So for I between 1 and k, theta belongs to S1, and we let hi theta prime to be just be the second type of handle body. Okay, and for I between k plus 1 and 2k, and theta belongs to S0, we let h prime I theta be h1 prime theta. Okay. Then we take the union HI just be the union of theta. Okay. So this is a family either over S1 or over S0. Okay. Now, what do we do? Okay, we consider the base B gamma to be S1 to the power of K times S0 to the power of K. So this is really the disjoint union of 2K copies of torus. Okay, this is slightly funny. You will see why I do that. Instead of considering a family over a single torus, I'm going to consider a family over 2K torus. Okay. How do I construct that? Well, so for each theta in B gamma, I'm going to construct a 4-dimensional sphere. It's just the union of H0 with HI prime theta I. Okay, so this is the handle body replacement, right? So the difference between this setting today and the setting yesterday is that we add this additional S0 copies, so that we don't we add actually some extra components. Okay, but in those but in those extra components, only part of the type 1 handle body replacement are done. Okay, so for example, if all these S components are 0, then we are simply not doing any type 1 handle body replacement. Okay, so basically the component we considered yesterday correspond to the component where this is 1, 1, 1. Okay, so this is just one of the components. Okay, and now, okay, so by putting this all together, we form a family E gamma, which is defined to be the union of all theta S4. Okay, so this is a family over this B gamma. Maybe let me put gamma here. Okay, and the fiber is S4. Yeah. And note that this is a decomposition of fiber, right? So we decompose the fiber into 2K plus 1 pieces. We decompose each fiber into 2K plus 1 pieces, and this will induce a decomposition of this bundle. Okay, so this bundle is also decomposed into 2K plus 1 pieces. Omega gamma I over B gamma. Okay, I hope this notation is clear. So I put, okay, on each fiber we have 2K plus 1 pieces, right? So we just pull the corresponding pieces together and form 2K plus 1 bundles over the same base. Okay, so this is a decomposition of bundles. This is the decomposition of basically the original bundle, right? But it also induces a decomposition of the configuration space bundle. And let's consider a 2-point configuration space bundle. We have this 2-point configuration space bundle, okay, over B gamma. This is decomposed into the union of 0, I, J, that's equivalent to K, omega gamma, I, J, over B gamma. Okay, where omega gamma, I, J consists of points you know, we always put the first coordinate to be infinity. So that's always fixed. x1, x2, such that x1 belongs to omega gamma I, x2 belongs to omega gamma j. Okay, so this decomposes the two-point configuration space bundle into like 2k plus 1 square pieces. Okay, right. Just imagine like this. Okay, so okay, and on the other hand, you see this bundle is over a k-dimensional torus, right? Well, a disjoint union of k-dimensional torus. But actually, each of these pieces is pulled back from some smaller torus. To talk about this fact, let me denote this. First, let me define KL to be S1 when L is between 1 and k, and S0 when L is between k plus 1 and 2k. And I'm going to be gamma ij, just defined to be the product of the intersection ij 1 2k L KL. Basically, you look at how many intersections are there between these two sets, okay? And whether the intersection belongs to the first k element or the later k element. So this space could be a single point if both I and j are infinity, are 0. From 1 to 2k, right? We do not include 0 because 0 is the trivial part, right? 0 is like we do nothing, near infinity. So, yeah. Okay, so this can be a single point if this is an empty set that corresponds to ij equals, both equals 0. Or it can be S0 if I equals j and greater than k. Or it can be S1, or it can be S0 cross S1, or S0 cross S0, or S1 cross S1. Anyway, so this is just some smaller torus than B gamma. Okay? And it's not hard to see from the construction that actually this bundle, you know, this bundle is actually pulled back from this smaller base. So basically, because you see here we are just taking the two coordinates only changes in the i's bundle and in the j's bundle, right? But we are doing nothing on the other piece. So it's really just pulled back from a smaller torus. Okay, so let me denote this by Pij. And this is actually, the total space is actually L. L is this. L belongs to this. Okay. So good. Now we are ready to give a definition. We say a propagator omega. So remember that omega is the 3 form on the 2-point configuration space bundle. Respect the product structure. If the restriction of omega on this each piece is pulled back. So maybe let me just write down the formula. If for any 0 less equal than I, j less equal than 2k, this the restriction of our propagator to this piece equals Pij star omega ij for some omega ij. Okay. In other words, on each piece, actually, you don't have a family over the k. Actually, on each piece is essentially just at most a 2-dimensional family. You just pull back from T2 to Tk. So it's natural to require that the propagator is actually just pulled back from T2 to Tk. Okay? In this case, we call the propagator respect the product structure. Okay? So that's the first requirement we want. And now we want a second property of a propagator. So what's the second property? Now let's consider, yes. So consider two different elements from 1 to 2k. Okay. We set omega ij to be 0 if there is an edge connecting these two vertices. Oh, there's no edge connecting these two vertices. Okay? And we set it to be mu e. I will define mu e if ij equals e belongs to. Okay? Where what's mu e? So suppose E is something like this. E is an edge going from I to j. And remember that we have a corresponding component. We have a Hopf link, right? So basically it's like this. And we have SIA, this is SJB. So this is a two-dimensional sphere, this is a one-dimensional sphere. Okay, and what's mu e? Mu e is actually what's mu e? Okay, mu e is defined to be oh, sorry, I forgot to. Okay, before that, sorry, I need to introduce one more notation. Okay, so remember that we have these differential forms on our standard handle body. Right? And that gives us, we can push forward this differential form and get mu1 a with 1 equals, sorry, mu1 I, mu2 I, mu3 I in a, which are differential forms over. Okay. So for type 1 vertex, okay, we can also push forward lambda 1, lambda 2, lambda 3. Push forward and get, let me still use mu. When I is between 1 and k. Okay, because when I is less than k, we have type 2 handle body. When I is greater than k plus 1, we have type 1 handle body. So we are using different differential forms. Okay, anyway, so and how do we define mu e? Mu e is just a pullback. It's just pi I star mu pi a wedge pi j star mu jb. Okay, so this is a differential form. This is always a 3 form on this product handle body. Okay. So basically, we are taking some specific differential form. Okay, for it. Now we set this Wij to be like this. Okay. Now a key proposition, which is actually the most technical proposition in Watanabe's paper, is the following. Proposition. there exists a propagator omega such that it satisfies the two conditions. First, omega respect the product structure. Okay, 2, omega equals Pij star omega ij, any I not equal to j belongs to. Okay. So basically, what is this saying? Basically, he's saying that, okay, we are dividing the whole C2 bundle into like 2k plus 1 square pieces, right? And this omega basically, so first it should respect some product structure, as I mentioned. And secondly, we're basically specifying all its value. Okay, let's say this is the zeros component. We are specifying all its value on here, not on the diagonal. Yeah, here. Okay, so we have some prescribed value on these blocks. Okay, building from the standard differential form on the handle bodies. Okay. Well, I don't think I have time to prove this. Let me just say proof. Idea of proof. Well, in the actual paper, it takes like 30 pages to prove this lemma. But let me just say that basically first we have this differential form and use the Ram theory to extend over the whole configuration space bundle. Okay, well, this is very sketchy, but yeah, basically you have some specific propagator on some pieces. You want to extend it to the whole thing, and you just use the Ram theory to show that there are no obstruction. Just like what we did in lecture 3. We have some differential form on the boundary. We can extend it to the interior because there's no obstruction from the Ram theory. Okay? Yeah, good. All right, now we are ready to do the final calculation, assuming this lemma. Yes. So we let gamma prime be another trivalent graph. Again, we assume it has no self-loop, no multiple edges, and no orientation reversing isomorphisms, just like gamma. Okay, and we'll identify its vertices with 1 to 2k, and then identify its edges with 1 to 3k. Okay, now we want to do the calculation. What do we want to calculate? We want to calculate, sorry, I have to erase some of this. What do we want to calculate? We want to calculate this configuration space integral, right? Yeah. And this is what? This is just the integration over C2 bar E gamma of this gamma prime pi E star omega. Right? This is the configuration space integral. Okay. Now, but we have already decomposed this configuration space into 2k plus 1 square pieces. So this can be written as sum. Oh no, it's sorry. What am I doing? This is n. Sorry. This is n. So really, this configuration space bundle can be decomposed into 2k plus 1 to a power of n pieces, right? It has n components. Each component belongs to one of the 2k plus 1 pieces. So really, you can decompose it into I1, what's n? Oh, sorry, this is n equals 2k. Yeah, so I2k. Second, okay, I haven't introduced the list notation, but I hope at this moment, this notation, the meaning of this notation is clear now. That means the first coordinate belongs to the I1 piece, the second coordinate belongs to I2 piece, and each component belongs to a specific piece. Okay, and yes, pi star gamma prime omega wedge omega. Okay, so I have to define what's this pi star gamma prime. This is a specific projection from, this is just the product. Right? Remember that how to define a configuration space integral. For each edge, we have a projection from 2k point configuration space to 2-point configuration space. So altogether, we have like 3k projections. We just pull them together and get this map. We pull back the wedge of these propagators and do integration. Okay? All right. Now, the first claim is that if there exists some lambda between 1 and 2k such that lambda do not belong to this I1, I2k, then this integration equals 0. Basically, yeah, this equals 0. Okay. Why is that? Okay, let's think about that. Why is that? Essentially, this is because, you know, this bundle, this is over B gamma. Okay? It's actually pulled back a smaller base, which is from, it's actually pulled back from a map from B gamma L doesn't equal to lambda KL. Remember that B gamma is like k copies of S1 times k copies of S0, right? So if lambda do not belong to this, that means we are not taking left handle for this is not involved at all. So this actually this family, this piece actually factors through a smaller base. Okay? And in particular, for example, if lambda is less equal than k, then the dimension of this is less than the dimension of B gamma. Then we are missing some S1 factors. So when you pull back, like from imagine that you pull back from a low-dimensional manifold to a high-dimensional manifold, and you do integration. Of course, you get 0. Okay, so this is 0, sure. And lambda greater or equal than k plus 1. In this case, actually, let me just say the different components. Cancels. So let me just draw this picture. Okay, let's say we have 4 components. Suppose you restrict to these 2. We know that when you restrict to these 2 components, it's pulled back from this direction, and when you restrict to these 2 components, it's pulled back from this direction. So that means if the integration of this and this, they are equal the same. with different sign, so they just cancel. And this is the reason why I don't want to just work with a single torus, but like 2 to the power of k copies of torus, because they can, on suitable pieces, we need them to be cancelled, to cancel each other. Okay, all right. So we see that this set, in order to get a non-zero number, this set must exactly be 1 to 2k. Okay, so it cannot miss anyone. So let's just assume this is I1 equals 1, I2 equals 2, I2k equals 2k. So let's just focus on this piece. Gamma prime. Okay, so now remember that, yes, okay, so what do we want to do? Okay, yes, so first of all, I want to write it back into the product. The wedge of E belongs to gamma prime pi E star omega. Okay. Now, and this is just okay, so basically that's just by definition. Now the crucial observation is that, remember how we define the propagator, okay? So by that technical assumption there, we see that omega restrict to this product piece equals 0 if ij do not belong to edge of gamma. Okay. So in other words, if there are some edges which belongs to gamma prime but not belong to gamma, you will get a 0 form here. So 0 times anything is 0. So you don't have any contribution. So the only thing we want to consider is the case that gamma is isomorphic to gamma prime, so that every edge of gamma is also an edge of gamma prime. In this case, it's just E equals ij belongs to E gamma. Pi I star mu I something pi j star mu j something. Okay, let me explain this. Okay, so for each edge basically for each edge, remember that the proposition says for each edge, the propagator has a 2 form, which is I something mu j something. Okay, right? For each edge, we have a 1 form, we have a 2 form and a 1 form, and we are taking like 3k. So altogether, there are 6k differential forms. Right? So we are taking, for each edge, we have a 1 form, we have a 2 form. This is organized in terms of edges, but we can reorganize it in terms of vertices. Okay, there are 3k edges, but we can just reorder it. The product of this equals the, okay, so there are 3k's, right? The product of this is equals the product of this, right? Altogether, there are 6k half edges, so there are 6k differential forms. You can, well, after the sign, you can just reorder it. We can just reorder it into like this. And that gives us what? That gives us I equals from 1 to 3k integration over this. Note that this is just a, okay, so note that this is just a handle body. It's just the product of this family handle bodies. Okay, so this is just, we can just integrate over each handle body. Mu I1 wedge mu I2 wedge mu I3. Okay, but remember that the wedge of these three differential form, when you integrate over a handle body, you just get 1. That's because of the triple intersection number equals 1. Right? So this equals 1. And this finishes the calculation that, let me just write down the final answer. If you integrate, if you do this configuration space integral over this, you get, the answer you get is the number of automorphisms on gamma if gamma is isomorphic to gamma prime and 0 otherwise. Okay, and this finishes the calculation of Watanabe. Basically, essentially, it's just using differential forms to turn the intersection number into like topological information. Okay, yeah, I think that's all I want to say today. Yeah, sorry for going over time. Yeah. Any questions? Okay.
I have a question about
Okay.
are those edge label, are those edge ordered automorphisms? Like ordered?
Yeah, it's the ordered automorphism. I mean, it's automorphism from gamma to gamma rho. Well, I mean, here we assume gamma has no orientation reversal orientations. So all these are orientation preserving. Yeah. If you have orientation reversing or if you have orientation reversing, then you just get 0 here. Okay, yeah, thank you.